Good evening, everyone. I'm Anish Ambedkar, PMRF and PhD candidate from Aerospace Engineering, ISC Bangalore. Welcome to this week's live interaction session for the NPTEL course Dynamic Behavior of Materials. This course has the course code MSA24ME102. In this week, we'll be going through, in this session, we'll be going through the week 8 content. Specifically, the content outline is given here. We first begin by defining different types of materials. Particularly, we are interested in studying structure of a material, the underlying microstructure, even the even at lower levels, say the underlying atomic structure and the arrangement, what sort of bonds there exist between different atoms and or molecules present inside that material. This ground level understanding of the material structure will help us understand how the material behaves at a macroscopic level. So, based on the laws of physics, if you have say certain you'll have certain atoms coming together, they can either form an ionic bond or a covalent bond, depending on whichever bond formation is easier. Then the material will sort of arrange itself into a particular configuration which tries to minimize the total energy associated with it, and based on that you get some underlying microstructure. So if I have to classify materials classification, I could do it in a couple of different ways. First way would be underlying structure. So whether the material is crystalline. Crystalline has atoms arranged in periodic order. Nice periodic arrangement of atoms. Right. So I'm drawing like a 2D grid as the representation, but this is basically your crystalline material. What we mean by this is it has a periodic arrangement of atoms. Next is another type of structure could be amorphous. In amorphous, you have a half facade atomic arrangement. So you could have say one atom here, another here, third one here. But then it's not necessary that this triangular pattern will be something close here. And there's no great order to this sort of arrangement. Crystalline can be further taken and it can be further extended to polycrystalline. Example of which is metals. Most metals exist when they can in nature in a polycrystalline configuration, which means multiple crystals coming together. Within each crystal, you have they have their own arrangement, but some more some more things happen when the different crystals come together at the boundaries. Another way to classify could be based on mechanical behavior. You could also classify it in like other ways such as electrical behavior and so on. So what particularly matters is your scheme of classification should be relevant to your choice of study. So since we are in mechanics, we're interested in mechanical behavior. So the most popular way to see this is by conducting a Uniaxial tension test. This gives you a stress strain curve. Uniaxial, which is of the form. We have two different types of curves. This one is brittle, the other one is ductile. What do we see that? Brittle materials, no plastic, no or very less plastic deformation, whereas in ductile materials, you would have significant plastic deformation. Right. So based on what structure you have, this mechanical behavior is informed. A rough classification could be, say, materials roughly classify as metals, ceramics. By combining different types of metals, you may end up with a composite material made up of more than one constituent. So metals are usually defined by their ability, so they are ductile and they are crystalline, often polycrystalline. Ceramics ceramics are brittle, however they can be both amorphous or crystalline. Polymers are usually amorphous or maybe have a very small range crystalline order. They can be both ductile or the ductility in polymers typically comes from configurational changes, so we're not looking into that. For this study, for this course overall, we are more interested in metals, and within metals, we have already seen that there can we can think of deformation as to have deformation to be of the classification could be elastic, another could be plastic. You remember the distinction, elastic deformation is one wherein the material returns to its original shape, whereas plastic refers to the kind of deformation which there is some residual permanent deformation. You can think of this to be like suppose I think most of you must have seen the thin plastics that are used in packaging, right? When we stretch it, initially when we pull it, there is a limit till which you can pull it and it goes back easily. But then if you stretch it beyond that limit, if you apply a loading greater than a certain critical loading, you see that the plastic uh, the plastic wrapper essentially starts extending much more than it could be, much more than it was originally. And then once you stop loading, the material doesn't go back to its undeformed shape. So that's the plastic deformation, a residual deformation that has been left behind. That residual permanent deformation. So particularly for plastic deformation, there are multiple mechanisms for plastic deformation in metals. There are there could be multiple underlying mechanisms. The first one that we looked at was dislocation slip. We'll get to in a moment. So, as we discussed, metals are made up of small grains. which are basically crystals arranged into random with random orientation, which come together to form the solid metal. Within these crystals, it may be there that the ordered arrangement isn't perfect throughout. There are some sort of defects that enter into the perfect uh, or the ideal arrangement. So within crystals, there may be defects, and these defects are usually generated or due to mechanical are there. So the easiest classification could be in terms of like how the defect can be represented as a say like a mathematical object, whether you can represent it with a point or say with a line or a surface or a volume. So I do this point zero D defects. An example of the same could be say vacancy defect. Within the vacancy defect, you could have say like a particular atom for the crystal not being present at its lattice site. Could also have line defects, example being dislocation. We'll look into that in a while. Third type could be say, surface defects, 2D defects. Example being grain boundary. The fourth type could be volume defects. Example being microvolts. So, a detailed figure for different types of these defects is in the textbook. I think it's figure 13.7, if I recall it correctly, from the Markner's textbook. If you want to look into that in detail, you could refer to that. Uh, suppose one way we could think of plastic deformation is suppose you have a periodic arrangement of atoms like this. Now, let small a be inter inter atomic distance within the same plane. Small b, and what you have is if we apply a shear load on this arrangement of atoms, you can think of as the atoms as the atom in the top layer T, bottom layer B. As the atoms in the top layer T start aligning with those in the bottom layer B, you will have increased resistance as if the shear stress is sufficiently large, will slowly overcome that resistance, and then your top layer T would move ahead by some distance, by the distance b to be precise, small b to be precise, and then land into another configuration where energy is minimized. So if tau is large, you have something like your bottom layer, assuming that your bottom layer remains fixed. will end up with a configuration like this. So the top player moves forward to another minimum energy configuration. So what we can think of the shear stress that resists this is, suppose I plot I plot how tau resistance of the atom uh, is a function of the displacement of the top layer, then I get curve that would not be an exact sinusoidal, it would be something like this. But for our approximation, we'll use the sinusoidal curve. Then you can, and suppose the peak resistance stress is given by tau m, then you can write tau resistance equal to tau m sine of 2 pi into x by a. It should be interatomic distance within the same plane, and then you have resistance is tau m sine 2 pi by. Suppose we move the first atom, or suppose we move the top layer to a slightly different configuration. So the angle becomes gamma. Gamma equals x by b roughly, where b is the interplanar distance. So if you move the top layer t by a small displacement x, then you have then the angle, the shearing angle associated with it would be say, x by b. For small x, we can simplify the above equation also as r is equal to tau m sine 2 pi x by a. For small x, we can simply write 2 pi into x by a. Now we know that tau and g are related to each other. So we have g into gamma equals tau r, using which you get g into x by b is equal to tau m into 2 pi x by a. Cancelling out, you get tau m is equal to g into g by 2 pi into a by b. So this is the estimated, this is the minimum shear stress required for permanent deformation, and usually you would have A and B to be quite similar, which means that the theoretical, well, strength of the material to resist a permanent deformation would be say something like G by 2 pi, which will be in the order of GPS, say maybe 3 to 30 GPa. So it's a very large shear stress required just to move this material and effect a permanent deformation. In reality, you have reality theoretical strength is much, much larger than your real strength, orders of magnitude. So why this is so? The reasoning for this is existence of effects within this. So the reduced strength of the material, uh, but we'll see how they also lead to ductility within metals. The defect that we are interested in here is the dislocation, which is basically a line defect corresponding to change in atomic alignment. Typically, you could have either an edge or a screw dislocation. So edge dislocation, I have to draw it something like. So I'm drawing like a cubic lattice, in which we are trying to see edge dislocation. So there is a break in this arrangement here. You can see this break in the arrangement is here, which corresponds to an extra half plane. There is an extra half plane. This is your edge dislocation. So, the plane is like inside the body. Like throughout, you can think for this particular example, it's not necessary that will always be throughout the material, but just for the sake of understanding, I've drawn it like through the width. Other type of dislocation is screw dislocation, wherein you have something like arrangement that goes like this. A little trickier to draw, but this portion, I should draw an axis. Why? So this portion, which is parallel to, whose normal is parallel to x-axis, that protrusion out of it, it's partial protrusion of plane out of the normal or perfect arrangement. That is your screw dislocation. So these are the two different types of dislocations. In particular, we are interested in the edge dislocation concerning our study for plastic deformation. So why do this? I'll draw it in the new page. How this dislocation comes into the question of plastic deformation? Suppose you have an edge dislocation. The atoms will always go to a place which minimizes, or rather, try to go to a place which minimizes the total energy of the system. And the shear stress is now applied to this. So this is my extra half plane. After deformation, if when tau critical, you can think of it that the atoms will move forward. The extra half plane will start bonding with this point, and this set of atoms will now form a new half plane. You could have, after a while, you could have an arrangement which looks like this. After another round of loading, you'll have an arrangement which look like this. So what now happens is your periodic arrangement is perfect inside, whereas those extra half plane atom ends up outside. So extra half plane ends up outside on the surface. What this will refer to as an atomic step. So this is about one kind of this is about exactly one edge dislocation. Now, in an atom, in a in a material, in a metal which has so many grains, which underlying which you have so many atoms arranged in a periodic manner, you can think that there will be a very large number of dislocations inside it. So, if we have lots of dislocation, we can have a combination of atomic steps can be seen, and this is basically your plastic deformation. As a result, you can think that ductility due to plastic deformation, due to dislocations. So ductility and plastic deformations are more macroscopic concepts. What we hope to get clear on is that how the underlying microstructure leads to a situation where you have dislocation, which eventually leads to say, plastic deformation, and that shows up as ductility in your uniaxial stress strain tests. So, if such dislocations exist, next question becomes how are they activated, how they move. So, we'll first answer how they are activated. We'll first answer at how they move. So, the first way is something called as a slip system. So slip system basically refers to slip plane and the slip direction. Slip plane is usually the closest packed plane in terms of number of atoms per unit area. Slip direction is similar but in a linear sense of closest packed direction. Atoms. So why these particular things? I think if you think about it, it's pretty obvious. Where would be this motion that we saw of shearing and moving ahead of each atom, each half plane across the atom, each half plane wherein that would be possible. So you can think of that would be only possible where the atoms are closely packed. So as a result, the dislocation has to travel less. That direction where the atoms will be most closely packed, that is your slip direction. And the plane is important in a similar sense that closely packed uh, atom would closely packed plane would similarly facilitate easy motion of easier rather relatively easier motion of atoms. So with this in mind, suppose we look at an FCC structure phase cubic center. I draw my axis here. X, Y, and Z coming out of the plane. This is my cube. So I am an atom here on the cube. Also have atoms here on the planes. Right. So we can see that the close can see that similarly draw atoms on the inside planes. Right. So this axis is so 8 at the corners and 6 on the centers of the faces. So the closely packed direction, closest packed direction is this is the phase diagonal, whereas the closely packed plane is shown with this closely packed plane is the 111. So for FCC, the slip system is 111. So and the slip direction is 111. So this refers to family of planes. This refers to a family of slip directions. So there are 12 such systems, 12 slip systems exactly within this. For each plane, you can think of three along with three this, and you can think of four distinct planes: one bar one bar one, and so on. Another one of these is how another associated question was how does loading play a role? Because while we are applying, where we are naming, and we can see logically that shear stress is the one that is required. In general, you may have any different random loading. So in that case, we are interested in understanding what is the resolved shear stress or the critically resolved shear stress. Suppose you have a beam of crystalline material. Let's say a force F, area A. So you have a single crystal beam under tension. And also similarly do it for compression. Suppose you are applying because it's tension force F, we assume that it will be, we have rather the force F, which is parallel to area normal for the cross section area A. Now within the crystal, you could have a slip system, a plane like this. So the closest back plane, which is the one that moves, and it moves along the uh, ideally that is the one that would move along the closest back direction. So you have suppose the area normal for this plane. This plane is itself in the plane normal itself makes say an angle. Plane normal itself makes an angle say phi, and then you have another slip direction, which is this way. Suppose this angle is lambda. This way. My single crystal beam, straight line, force F, and cross section area A. Then we look at slip system within this beam. So suppose it's oriented at an angle P from the applied force, and the slip direction is oriented at an angle lambda from the applied force. This is suppose like the 111 plane normal, or FCC, you can think of this as the 111 plane normal, and this you can think as the 1/10 direction. An example, that's all that is. So you can write your normal force to be Fn normal force to uh, slip plane. Fn is equal to F cos P, shear force to the slip plane, as Fs is equal to F cos lambda. Right. So this is what we get as the shear force and the area of the slip plane. As is equal to A by cos P. So again, simple geometry, trigonometry that we are using. What this is tell you? Therefore, the normal stress on shear plane is Fn by As, which is F by A cos square phi, which is sigma cos square phi. Sigma is the applied stress. Where is shear stress of S, Fs by As, should be sigma cos phi cos lambda. This cos phi cos lambda is called as the Schmidt factor. And you can see that Active slip system. So when this force is applied, dislocation will start moving in a slip system. That is what we mean by active slip system. Active system slip system is the one which where slip factor is maximum. So you could have multiple slip systems as we just discussed, but the active one, the slip system which gets used for the dislocation to move forward is the one with the largest load factor because that is the slip system for which the shear stress tau is the highest and that easily facilitates motion of dislocation. There are other types of plastic deformation, other mechanisms of plastic deformation. These include plastic deformation. This include martensitic transformation, which is widely seen in shape memory alloys, wherein the material undergoes a transformation from between two different underlying configurations, and that leads to, in a bit to minimize its overall energy. That leads to typically some changes in volume, some small changes in volume, which may uh, be permanent. Another mechanism is called as twinning. Particularly here we uh, refer to mechanical twinning, whereas where uh, this mechanical twinning is also caused due to shear stress. But what happens is that the crystal structure itself gets deformed, so displaced. So suppose I have a material like this. Now I'm talking about mechanical twinning. After a while, what happens is write this now. After a while, what happens is the entire crystal structure across one plane gets moves around. So you would have something like so. This is called as the glide plane. So your entire crystal structure moves above a plane. It, it glides, so to speak, into a different configuration which minimizes energy. And then this process can keep on repeating based on your applied load. So the thing here to notice that there is usually reflective symmetry across. There is reflective symmetry about the glide plane, which is why like the twinning comes about. But it's usually these mechanisms compete with each other. Say twinning and shape will compete with each other, and twinning would require you can think of it by here only by looking at this diagram, this crude rather representational diagram that because the entire crystal structure has to be displaced above the glide plane, a lot more energy is needed. So it doesn't easily occur as much as dislocations would, and which is part of the reason why uh, within an FCC structure, right, where you have such closely packed atom, dislocation slip is the much more preferred mechanism for plastic deformation. Whereas if you move to a different system, say like hexagonal close pack, therein you could see more twinning easily. And twinning is usually facilitated by high strain rate deformation as well as low temperature deformations. In those cases, twinning becomes relatively easier, so to speak. So we spoke about deformation, but while dislocations do impart ductility, they also weaken the crystal. Dislocations impact ductility. They also, but also weakens crystal. So how do we go about this? So the easiest way you could think of it is say theoretically remove all dislocations, right? But this is extremely impractical, as any mechanical or heat loading would again just go back and generate some more dislocation. So how what do we do? So practically practical approach involves resisting resist dislocation motion. So we'll look at a few examples of the same. First one is strain hardening. So what is strain hardening? When we look at a stress strain curve, even if it's a stress strain curve for a ductile material, there is usually a linear elastic region till the yield point. Then after that, the stress increases, but there is much larger deformation. So there is an onset of plastic deformation. So what happens here? So as your epsilon increases, as your strain increases, number of dislocations increase. So increase. This leads to a traffic jam situation or dislocations. Right. So because the number of dislocations has increased so much, they're all sort of competing to move ahead as stress is applied, and that makes it difficult for in turn that makes it difficult. And because the material has already undergone so much strain under so much mechanical loading, number of dislocations also has increased. So it's a double whammy. And what we end up with is strength of the material increases. Because of this traffic jam sort of situation, there is a change in the stress required, shear stress required to move dislocation changes as per uh, changes as per dislocation density. You can think of it as how many dislocations per unit of the material. So you have tau is equal to tau naught is a root. So this is your dislocation density. So this is one way. So this is the more natural way, so to speak. Another thing is solid solution strengthening. What do we have here? Suppose you have an arrangement of atoms, dislocation. So this is how it looks like. This is your say extra half plane representing your edge dislocation. Suppose I put up this is my solute atom. It's a physical barrier for dislocation motion. So this is your solid solution string, wherein to move the edge dislocation, it becomes physically again it becomes physically much more harder because there is no space for it to move. Third type would be grain bond string. So in grain bond string, you have suppose you have atoms arranged like this. Then we'll add a dislocation. Because this is your grain boundary. So an extra half plane corresponding to image dislocation. You could have another arrangement of atoms going like this. So grain boundary. What happens here is dislocations move inside the grain, but then they pile up at the grain boundary, which this ends up resisting, piling up ends up resisting plastic deformation, which means strength increases. So a more roundabout way to get at the same place where we are trying to resist dislocation motion. This grain boundary strengthening is particularly well known and is formulated in a formula called as Hull-Petch law, which is a relation between yield stress and grain diameter. So it looks something like sigma y is equal to sigma naught k by root d. D is the grain diameter. So this is a rough formula again, not rough. This is a phenomenological formula, empirical relation that we have arrived at. Grains may not be perfectly spherically symmetric. So the grain diameter is an approximate measure, and what you have is because the dislocations pile up at grain boundary, you can think that if the grain size is smaller, the number of dislocations that can move up to the grain boundary is lesser, and as a result, the pile up starts quicker. If the pile up starts quicker and the dislocations cannot move around, which means that your yield point, wherein your plastic deformation onsets, that gets pushed a little ahead. So, by this law, as the grain size becomes smaller, your yield stress gets higher. So it's not like a lot of empirical relations. It's valid for a good uh, number of observations, but we should not think that we can make the grain size indefinitely smaller because that would have add another sort of effects. That's an entirely different area of study in nanocrystalline materials. Okay, the final part. So why we did all this is again we want to get back to our dynamic deformation of materials and to get a more appreciation of little more appreciation of what's happening. We looked at materials part of it. Now, uh, in the materials part, we look particularly closely at structure, kinds of defects, and how they influence macroscopic behavior of material. With this knowledge in mind, we'll just keep it in the background for a while. We'll move into this new topic, which is shock wave induced phase transformation. So, in shock waves, we write them as SHW for short. Shock waves. You have large number of physical. You can have a large number of physical and chemical changes. So, this was first reported by Michal in 1954, and what we had here was a polymorphic phase transformation. I'll write phase transformation as PHT in short. Phase transformation of iron at 13 GPa shock wave from alpha, which is BCC, to epsilon, which is KC. So there was a shock wave in this phase transformation, and next up was another important one was Carly and Jamieson, 1961. They reported graphite to diamond and phase transformation due to shock waves and observed micron sized diamonds. May not be very useful for a ring, but particularly useful in the industry. Third one, so Dremin and Brems, 1960, they have written a summarized software phase transformation, wherein they say that shockwave has a lot, like it has a high amount of energy which gets dissipated during propagation. So what happens to this energy leads to physical and chemical changes, yes, chemical changes within the material. Example of which is the polymorphic phase transformation. Could also have chemical synthesis. Similarly, it could equally well have chemical decomposition. Could have say formation of defects. So this dissipation, right? This shock wave passes through. So there is usually very short duration, and there can be development of temperature gradient, which is seen due to void collapse. And their interfaces can also melt. Powders can also join. So a large temperature gradient for a very short amount of time can cause havoc in the system. We'll now move into something that's more relevant is phase stability. So we talked about phase transformation, right? So transformation means what phase transformation would mean that the material undergoes changes from phase one to phase two. But why would material do so? So phase stability it is determined by thermodynamically speaking, it is determined by Gibbs free energy. We could have the condition of constant pressure or constant temperature. So within the shock wave for that very small duration where you have the peak pressure, the high rise plateau that you have seen in a shock wave profile would theoretically be considered high pressure. Similarly, during the rise, when suddenly a lot of energy is moved into material and a lot of volumetric changes would happen. There will be an associated temperature rise, and the temperature rise will exist again steadily for a very small amount of time. So both those cases, constant pressure, constant temperature could happen. So why phase transformation happens because any system tries to wants to minimize its free energy. The Gibbs free energy is written as thermodynamic enthalpy minus temperature into entropy. It's nothing but internal energy plus PV minus T into S. Therefore, change in the Gibbs free energy is B plus VdV plus VdP minus VdS minus SVT. From the first law of thermodynamics, we know that conservation of energy, which is work done by the system, change in internal energy of the system is input heat minus work done by the system. The second law of thermodynamics concerns itself with reversibility. Reversibility. It mentions that entropy or a major disorder within the system keeps on increasing in an irreversible process for the entire universe. So here you have del Q is equal to TdS. This is for actually for a reversible process. For a reversible process, which is what we use here. So we assume a reversible process. Once we plug this in, you get Tg is equal to del Q minus Td Vdp minus TdS. Assuming the reversible process, you have TdS minus PdV. There's another PdV here. This PdV, this PdV. This is my VE, PdV, SVDP minus TDS minus STT. DVP cancels out SCDS, TDS, TDS cancel out. So you end up with VG is equal to VDP minus SVDT. So, this is equation for change in the differential for the fixed free energy. So consider a case where you have constant E, which means dt is 0, so isothermal process. You have dg is equal to vdp, which means dou g by dou p at constant temperature equals to 1. So from this equation, if system wants to minimize free energy G, you have the case that as P increases, system phases with lower volume. Second case is constant pressure. So the constant pressure case associated, you can think of it associated with the high rise of the shock wave profile. Constant temperature will occur, or the temperature rise, you can think of it will occur a little, with a little delay as respect to pressure uh, going through the system, because during dissipation, that is when this loss of energy would be converted to different components. Eg is equal to minus SDT for the constant pressure case, which means partial derivative of G with respect to T at constant pressure. So T minus S. So as T increases, you favor a rather system favors a phase with higher values of entropy. So if I were to draw this in a diagram, T versus P diagram, so suppose this is the transition pressure. This is my phase beta, this is my phase alpha. So at P is equal to Pt, transformation occurs. P less than Pt, beta is the preferred state, P greater than Pt, alpha is the preferred phase. So if why this is so, if we look at the, we go a level deeper and we take partial derivative of G with respect to P, isotherm, you have beta phase transformation, then you have alpha. Right, so there is a delta V, this is continuity, this is volume change, phase transformation. So this is called as, this whole thing is called as first order phase transformation. And examples of the same could be melting, solidification. So uh, there is another type of phase transformation involved, which is called as second order phase transformation. Herein there is no discontinuity in volume, so to speak, that we saw in the first partial derivative of Gibbs free energy with respect to pressure. Where there is generally some discontinuity associated in the second partial derivative. Such a transformation is much more difficult to quantify properly. So though that is a second order transformation. Next, I think that's a little beyond this. Course, the next final part of this is we again go back to our phase transformation. Phase transformation. And think of we can think of Gibbs free energy to be it's a, it's a function of two variables, pressure and temperature, right? So you can think of it as a surface on a 3D coordinate axis. And for the two phases, you can write G1 of PT and G2 of PT as my uh, surfaces corresponding to two phases. So we are considering the case where you only have two phases in the material. And for both of these phases, you could in theory evaluate what the Gibbs free energy surfaces look like as a function of pressure and temperature. And we also know that partial derivative, small change in G is nothing but rho G by rho G of T into dP. Yes, because it's a two variable function, right? So we take partial derivatives and multiply it. So for the two surfaces, we define a combined surface G1 minus G2, and we are interested where this surface basically it comes as same. So at phase transition, the small changes in both of the phases surfaces will be the same. So you would have dg1 minus dg2 is equal to 0 phase transformation. dg1 minus dg2 can be written as rho g1 by rho g rho g by rho t minus rho g by rho p2 t dp plus rho g by rho p minus rho g by rho p at p for h2 into dt. Right. 0 is equal to p1 minus v2 times dp plus minus s1 plus s2 times dt. Rearrange this equation, you end up with rho p by rho p equal to delta s by delta v. So another interesting equation associated with phase change transformation. So I think that covers what we have for what we have for this particular lecture. If there are any doubts associated with it, we can take them now. If not, then I think we'll close today's session. Thank you for attending and or watching it on YouTube. I'll see you again in the next one.